Hi, this is a continuation of the previous problem, but it's really a whole new problem in and of itself. It shows us how to use Newton's universal law of gravity when you have interactions between more than just two objects. So read this one for a moment, and then we'll go ahead and set this problem up. All right, so in this case, we've tried to simplify things by making the moon, sun, and earth all aligned, as which happens when you have a solar eclipse. And we've also aligned the spacecraft. So let me go ahead and draw a picture of what this is going to look like. So here's a picture of the arrangement in space of these objects as described in the problem. And remember that we're going to focus on the net gravitational force that acts on the spacecraft due to the other objects, right? We know that the gravitational force that we need to use here is Newton's universal law. So here's the magnitude, right? Given, and the direction attractive along straight line between M1 and M2. So we've got a number of objects that are going to interact. So the magnitude of the gravitational force, of course, in any case is always capital G. One mass, a second mass, two masses interact, and R is the distance between the two. We're going to have three interactions with the spacecraft, so let's go ahead and write those three down. Okay, so I've written down the gravitational force magnitude that's acting on the spacecraft due to its interaction with the Earth, the Moon, and the Sun. I've abbreviated spacecraft FC there. And for the masses of the big planets and things, I can capitalize it, right? But you can see the notation. Now we need to figure out what is the direction of these force vectors so we can draw the forces right on the spacecraft. So let me start with the Earth. As we saw from the summary of common forces, for universal law of gravity, it is an attractive force along a straight line between M1 and M2. So Earth is going to be pulling the spacecraft towards it along the line connecting the two. So this is your force on the of gravity between the Earth and the spacecraft, right? Similarly, for the Moon, it's going to be attractive along the line between them. So we've got this one here. Force of gravity between the Moon and the spacecraft. And finally, for the Sun, again, it's attractive. The Sun will pull it along the line, and so we could do it maybe like this. Force of gravity between the interaction of the Sun and the satellite, or the spacecraft. Now, I don't know how long those arrows are, right? We're going to figure that out when we plug the numbers in here, and then we'll get those values, right? And let's go ahead and do that right now. I'm going to go ahead and use the information from Wiley plus back matter again to get all those numbers and plug them in and calculate them. All right, so I looked up G, Newton's universal constant, and I looked at the mass of the Earth, mass of the Moon, and the mass of the Sun. And I put in the mass of the satellite, of course. Notice I haven't yet done the radii. How are we going to measure those? Well, turns out that the spacecraft, it's equally distant between the Earth and Moon, okay? So if we can figure out what the distance is between the Earth and Moon, we can take that distance, R, Earth-Moon, divide by 2, and that's going to work for both the Moon and for the Earth. So we can go ahead and put those, essentially, this guy right here, right? And this guy right here. Those are both going to be equal to that, right? And for the Sun, well, basically we have a measurement for the distance of the Sun to the Earth. And, well, if we draw that picture, that line, for example, right? From here to there, there's the radius of the Sun to the Earth, or the distance of the Sun to the Earth. We're going to just use that number for the spacecraft, because we know this drawing is not to scale. This is really, really far, this part here. And so anything between the Earth and the Moon is small compared to the Sun's distance. So we'll use the Sun's radius to the Earth for this one down here. And so if we go look those up, let's see here. Mean distance from Sun, there's the bottom one. Mean distance from Earth, the distance between the Moon and the Earth, we'll divide that by 2, and that goes for the top two. So we've now put in the relative radii for each of these halfway between the Earth and Moon, halfway between the Earth and Moon, and the distance between the Earth and the Sun. Now we're going to go ahead and put all these numbers into the calculator and see what we come up with. And so I've plugged in the values and come up with the numbers that you see there. And I was a little surprised to see that they're pretty small, but it does make sense because as we see Newton's law, it falls off the further away you are, and it falls off by the power squared. So we can see here that if you're far enough away, gravity is kind of weak, and the fact that Newton's gravitational constant is to the -11th tells us that even though gravity is dominant when we're right next to the Earth and we're on the surface, it's actually a weak force compared to other forces such as electromagnetism and the nuclear forces. And we can even check this. Check out the exponents. Just do an order of magnitude calculation here. This would be times 10 to the third here, right? And this is 8 and squared, so this is going to be like 16 here. If you just look at this, right? -11 plus 24 plus 3, and then we're dividing by 16. That means -16. Well, if we add that all up, we get 0, right? And that's like 10 to the 0. It's roughly 1. 12.9, it's close, right? So order of magnitude kind of works out. Why don't we check this one over here? -11 plus 22 plus 3, and then we got again on the bottom -16. It's going to be the same thing here. Let's see, -27 plus 25, right? -2. So that's going to be fractional. It's kind of like 10 to the -2. We're close there. And you can do the same thing with the sun. Kind of interesting how it works out. So at the end of the day, we have these relatively small values for the magnitudes of these forces. And now these magnitudes that we just calculated, right? Those are the lengths of the vector arrows that we see here in our picture. So we can go ahead and draw those as a free body diagram now and go ahead and do our vector addition to get the net gravitational force. So here is our original picture, and we look like the longest arrow is the Earth. The purple one's the shortest, the Moon. Maybe we can just readjust this a little bit. So the Moon's kind of like our little short guy here. And then the Sun is something in between the Earth and the Moon, right? So that's kind of what it looks like. And if we want to draw a free body diagram, right, all we do is we draw the exact same thing here. This one almost you don't really need to do, but let's go ahead and just do it anyhow. So here's our free body diagram, and we're lucky because these are all along the same line. Let's go ahead and put an axis there, plus x. All we really need is the x-axis, right? And so if we want to go ahead and make a little table here to organize our work, we can do that. So here's a little table that we've got, and we can already put in all the zeros for the y-axis for all these. There's none. And then we need to put in the numbers for the x with the appropriate signs based on the free body diagram. And below there I've just shown the sum of all the gravitational forces, right? Of course it adds to 0 here, and we got to look at the numbers for the other ones to fill our table in. And it looks like for Earth spacecraft, that's going to be in the negative direction, right? So that's a negative, and that's going to be 12.9 newtons. For the Moon spacecraft, that's going to be positive, and it's going to be 0.158 newtons. And for the Sun spacecraft, that's going to be a positive again. It's going to be 7.08 newtons. And let's add those all up to it. Adding these up, we get minus 5.66 newtons. And so that is your net force in the x direction. If we want to get the magnitude, F net gravity on spacecraft, right? That's just what I'm calling the magnitude of this vector that I wrote there, the sum of all the gravitational forces. Well, since we only got one component here to worry about, it's just going to be the magnitude of that one component. And so we come up with an answer here of 5.66 newtons. So you could see with the universal law of gravity, it's still a force. And when we're looking at how forces act on an object, we still use the same idea of adding up the net force. In this case, we just have a longer formula for determining the magnitude, and we need to use the direction, always attractive along the line of interaction as well, to get the direction there. You'll have a couple problems like this in a future homework which are very similar.